Okay, so today we are going to look at one of the kind of odds and ends that I'm going to throw into our Calculus 1 curriculum that are on the AP exam / that are just really useful tools. So one of those is L'Hopital's rule. This is applicable to all kinds of situations. Specifically, L'Hopital's rule is used in limits mostly. It's used for when a limit is indeterminate. And there's all kinds of indeterminate forms. So for Calc 1, we're just going to focus on the indeterminate forms 0 over 0. So if you have a limit that's undecidable or indeterminate and it's 0 over 0, then you can apply L'Hopital. L'Hopital's rule says something really simple. So also, if you have the indeterminate form infinity over infinity, you can apply L'Hopital. Now, in Calc 2, we'll discuss other indeterminate forms. You can't decide what this is. Sometimes it's 7, sometimes it's 0, sometimes it's infinity, sometimes it's 3.5. Same thing for this. There are other indeterminate forms. For instance, 1 to the infinity. 1 to any other power is 1, right? But 1 to the infinity can be different things. Also, 0 to the infinity can be different things. And another real big classic is infinity minus infinity. Infinity is not always the same size as itself. There are different sizes of infinity. Hence, when you subtract infinity from itself, sometimes you get something concrete like 7. Sometimes you get infinity left over. Sometimes you get 0. So L'Hopital's rule applies to all these different forms, but we're going to be focusing on these ones that are nice and simple in Calc 1. Even in Calc 2 or in any other calculus situation, guys, in any other calculus situation, if you run into one of these other forms, you're going to need to convert it using clever algebra into this before you can actually apply L'Hopital. So no matter what, you kind of have to get this one way or another. Okay, so what does L'Hopital's rule actually say? So I'm going to put what L'Hopital's rule says right here. It can fit in this little tiny spot. So it says if you have a limit as x approaches some value of one thing over another thing, so pretty much L'Hopital only applies to rational or fractional situations where you have a ratio of functions like that. If you don't have a ratio of functions like that and it's like one of those other forms, usually you just like make it into that. So if you have that and it's equal to 0 over 0 or infinity over infinity, then this is actually equal to the limit as x approaches that same thing of the derivative of the top over the derivative of the bottom. And then you just look at that limit, and as long as it's not indeterminate, you evaluate that limit. If that limit is still indeterminate, you L'Hopital again. And you can use L'Hopital repetitively until you get to a limit that you can do. Okay? So that's the idea with L'Hopital's rule. Let's see it in some concrete examples. So here's the first one. So first, you want to just try to evaluate the limit like we've done. Conceptually, it's not the best, but remember, to do the limit, what is the first thing we always try to do when we do a limit usually? We just like substitute in, just like kind of plug in, right? Now that's not a great way to think about limits because remember, limits are all about approaching a value and not being a value, but we always just try to plug in and see if it works first before we do anything else, right? So if I plug in right now, what do you get? Yeah, because this is going to be 1, right? 1 minus 1 is 0 over 0, so this is 0 over 0. So, can I use L'Hopital on this limit? Yeah. You always got to check this, though, and don't be too quick about it. Make sure that it fits the situation, because if you use L'Hopital in a situation where it doesn't apply, you definitely get the wrong answer. So, it does definitely apply here, so I'm going to say this is equal to the limit as you approach 0, and derivative of the bottom is easiest derivative ever. And the derivative of the top is chain rule. Minus 0. Constants go away, right? Okay, so now we're going to try to evaluate that new limit. As you approach 0, well now this isn't going to go to 0, right? The top's going to go to that, which is 2. Done. So that limit is 2. So notice, if we didn't have L'Hopital, that problem would be difficult to do with clever algebra. You could do it that way. In fact, you could also do it by just thinking about as you approach 0 and plugging in values that are really small, like 0.0001. But L'Hopital gives you a really easy mechanical way to do something like this.
Please call it La Hospital.
Yeah. Sorry. I'm not that un-French. Okay. So if we approach infinity for the natural log of x over x, the natural log of infinity, it grows slowly, but it's still going to go to infinity eventually. That's clearly going to be infinity. So I can apply L'Hopital. The way I like to usually say that with notation is I like to go like this. So I really should have done that right here too.
AP Stats is starting.
That was pretty blunt.
Uh-oh, SpaghettiOs, maybe. Okay, so help me with L'Hopital, guys. Yep. And then you can apply the limit and say, you said it's just 1?
1 over x.
Right. Right. So I don't even need that, right? You're right, Henry. Let's do it just like that. It simplifies just like she said. So if you approach infinity, now what happens? It goes to 0, right? You can think about that graphically if you want to think about the 1 over x function. And as you approach infinity, it goes down to that 0 asymptote. I think a better way to think about it is just the size, right? If you have 1 over something really, really, really large, remember that that goes to something really, really, really small. And if you actually go to something really, 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 really large, like infinity, it goes to 0. Okay, so there we go. How about this one? Let's see, can we apply L'Hopital or not? Oh, I'm just going to plug in, so on top, what am I going to get?
Infinity squared.
Infinity squared, so infinity. Is infinity squared a different size of infinity?
Yes.
Actually not, but there are different sizes. Okay. So if you plug negative infinity here, what do you get?
Either positive.
So that's going to be infinity over infinity. So we can L'Hopital this one too. So we'll say that's going to be equal to the limit as I approach negative infinity of what?
2x over negative e to the x, to the negative x.
You got it. Nice. Okay, so now we're going to get what? Negative infinity on top? 2 negative infinity, right? So that's negative infinity.
If it's negative infinity times that.
And down here, what do we have? Negative e to the positive infinity. So these negatives kind of cancel out, and we still have infinity over infinity. That means we can L'Hopital again. Sometimes you might have to L'Hopital 3 times or 4 times. Not very common, but it happens. So this is going to be 2 over.
Positive
Yep. So now if I evaluate the limit, what happens on top?
2 over infinity.
It's 2 over infinity now, right?
Negative infinity.
So that's going to be no positive infinity, negative, negative. So that's going to be 0. And that's the answer to that one. Okay, let's look at just a couple more. All right, just a couple more examples. Before we get to these examples, I wanted to talk about one of those other ones we had a second ago. I think it was the second problem. So we came out that this one did what? What did it go to?
Infinity over infinity.
Exactly, so it went to 0 eventually. This was an example of a problem that you could totally do another way, and maybe even easier than L'Hopital. L'Hopital's pretty easy, but that one I can just look at and say the answer immediately. How do you do it that way? What's another way to do that problem? Very important for science especially,
Which science?
like all sciences.
Oh.
All sciences use this kind of rhetoric. Maybe all is too broad, but the big 3 use it in different places: biology, chemistry, physics. As you approach infinity, what's the order of magnitude of these? This one has
It should be.
a small order of magnitude because it grows slowly as you approach infinity. This one is a line, not the fastest order of magnitude, but which one has a bigger growth rate? The bottom. So if the bottom grows faster,
It's also equal to 0.
then it's eventually going to be like something small over something big. And as you get to something really, really big, that's going to go to 0. So remember, you can also evaluate infinite limits with order of magnitude arguments. That's a good way to check ourselves on that. All right, let's try L'Hopital another time. If we can, let's see. If we plug this in, then we get what? Tangent of 0 minus 0 over 0 cubed. Tangent of 0 is, of course, 0, because that. So yes, I can use L'Hopital and say that this is equal to what?
Oh, I missed
Help me.
it. The secant of x minus 1. Right? Yes, squared x squared minus 1. Divided by 3x squared.
Okay, what's that equal to?
It's still going to have a 0 over 0.
Secant of 0 is 0 because cosine of 0 is 0. So, oh, no it's not. What is the cosine of 0? It's 1. So that's 1 squared minus 1 over 0, which is 0 over 0. So another L'Hopital is legal.
Not legal, it's necessary.
There's other ways to do this. So, I'm going to have 6x and I'll write it like that to show you the chain rule, hopefully. Times what?
Times the secant.
Hopefully we know this if we're at this point in calculus.
That still ends up.
So I'm going to simplify that before I do anything else. That's going to be 2 secant squared tangent of x over 6x. Yes, we've got 0 on the bottom. If we go on top, that's going to be 0 and that's going to be 1, so we still have 0 on the top as well. So I'm just a little bit more involved. So finally, I can L'Hopital one more time. I really should be showing my L'Hopitals the whole way, right? So I should say this came from L'Hopital, this came from L'Hopital, and this is going to come from L'Hopital.
We're going to have to use the.
And I am. This is going to be an ugly derivative. So let's see. We've got 6
First thing times the derivative of the second thing. So 2 secant squared x
first
squared x, which is 2 secant 4
times derivative of second. Yep. Plus
second thing.
second
Derivative of the first.
derivative of first. And didn't we just have the derivative of the first?
2 secant.
It's right there, right? So you could just like copy and paste it right here, right? So 2 secant squared. You got it. Okay, so that looks pretty ugly, but as we approach 0, the bottom is 6. I guess I'll use my blue from last time.
Which means it's going to be.
And the top, we've already done that calculation, so this is actually pretty easy. The secant was 1 and the tangent was 0 at 0, right? So that's going to be 2 times 1 squared times 1 squared plus, it's not going to be 0 anymore, plus nothing, because either one of those goes to 0, right? So the answer is 2/6 or 1/3. This limit approaches 1/3 as you approach 0. Okay, so that was a case where we had to use L'Hopital 3 times. Last question for today is this one. Okay, so what's different?
Pi to the negative, so on the left
From
side.
the left.
From the left side, right? Sorry, I get backwards. For you guys, it's from the left side, right? So this is no different. You just do it the same way. Remember, if it's from the left, you can still think about just kind of plugging in to begin with. And what do you get? The sine of something close to pi. Technically, we're coming from this side, so it's like, if you really want to think about it, it's like 3.14 minus a little bit. But really, if I cut pi at 3.14, isn't that kind of approaching it from the left already? Or you could just go like this if you want to be, you could go like, that would really give you a good idea. I'm not even going to think on that level yet. I'm just going to think about plugging it in. Okay? So I've got 1 minus the cosine of something close to pi. Let's just see what happens if we just straight up plug it in, kind of even ignore the approaching from the left part. So sine of pi, pi is right here, right? Sine is 0. Cosine is -1, so you get 0 over . So should I apply L'Hopital? No, the answer is 0. If you don't believe it, you could go, of course, check this on your graph or something like that. But notice, don't be too gung-ho to just start applying L'Hopital. In the worksheet I gave you, and in most situations, sometimes L'Hopital will apply, sometimes it won't. Let's see what would have happened if we'd apply L'Hopital to this rule without paying attention. So if you apply L'Hopital to this problem, what do you get? Cosine over sine of x, right? If we plug in pi, then we get
So it's just going to be negative 1 over 0.
what's that?
0. Oh yeah.
Is undefined the same as 0? No, they're like totally opposite things. So you can see that if L'Hopital doesn't apply, if you don't have something that's 0 over 0, infinity over infinity, or at least something that you can turn into one of those forms, you can't apply it or you'll be wrong. So careful on that. I'll see you next time.